In the first part of this playlist, we created a notebook instance in AWS Sagemaker. In second part, we trained in Google Colab. We trained the CIFAR100 dataset with Resnet34 model. We also did TensorBoard logging. In this part, we will be training and inferencing CIFAR100 dataset through a Python script in AWS Sagemaker. As part of this, we will be creating a notebook inside the notebook instance. We will be preparing a Sagemaker estimator with multi-GPU instance. We will be using a Sagemaker instance which offers 4 GPUs. We will be training and testing the Resnet34 model using this Sagemaker estimator and using the Python script that we will prepare. We will save the checkpoint and we will also log the training details to weights and biases. Then we will do inferencing with a CPU only instance. The CPU only instance is different from the notebook instance that we created. If you remember, notebook instance that we created was also CPU only, which was ml.t2.medium. This inferencing CPU only instance will be different. So in total there will be 3 SageMaker instances that we will be making use of. One is the notebook instance, which is ml.t2.medium, which was a CPU only instance. Then for training we will be using another instance which will be offering us 4 GPUs, and inferencing again we will be using a CPU only instance, but will be different from what we have used to create notebook instance. So if you go to Amazon SageMaker and notebook instances, we can see the notebook instances that we have already created. So this one MLO S9 CIFAR100 PLv3, this was the notebook instance that we created in previous video. Now we can see the status is in service, and if you click on open Jupyter, it will take us to the home tab. So here I have already created the notebook and executed it. So in this video we will be walking through the contents. So this was the notebook that I have created for this session. So let us walk through the contents. If you notice on the right, I have created this notebook with Conda PyTorch latest P36. We will do necessary imports. We will be importing SageMaker and UOID. We will be creating a checkpoint S3 path. This will be the Amazon S3 path, AWS S3 path, where our checkpoint for this current training will get saved. We can refer this checkpoint S3 path later as required. Here we are just checking if there is an GPU available or not. If you remember, we created this notebook instance with ml.t2.medium, which is a CPU only instance. So it is confirming that it is a CPU only instance. We are installing PyTorch Lightning in this notebook. Reason why we are doing this is we will create a CIFAR100 data module just to ensure that our train loader and validation loaders are working correctly or not. Why we are doing this is, once we move into the SageMaker instance, and if there is some issues with during training, we will incur a cost. So we want to avoid that and just need to make sure that everything is working fine before we hit the training. So this CIFAR100 data module is inherited from PL Lightning data module. As we have seen in the Colab notebook, we are giving the data directory as /data. If you notice, there is a data folder which got created, and if we check the content, we can see that CIFAR100 Python is already downloaded, same as we have seen in the Google Colab example. Rest of the code is exactly similar. We are having prepare data method, setup method, train data loader, validation data loader, and test data loader method. Next, we are going to make use of this data module. We will be creating train loader and test loader, and we will just define ImShow function which will show the images that are coming out of train loader and test loader in matplotlib, and as we have seen in the Google example, we have defined the unpickle example to get the fine label names. In case if you miss to see the Google Colab example, I would recommend you to go through it so that you will better understand why we are using this unpickle and what is this metadata fine label names. We are just confirming that our test loader is working fine. The images are coming out correctly, first being mountain and last being mushroom, and we are just showing the train image as well. Here we are giving a batch size of 32. In Google Colab, if you remember, we gave 64. Here we are giving 32. So the first one is shown as bottle, and maybe third one is shown as mountain. So looks like our train data loader is also working fine. Next, we will prepare the inputs. Again, we will be making use of the data that is loaded in this data folder. Then we will be installing, we will be importing this PyTorch. Here we will be making use of spot instance, and we are giving this max run and max wait variables here. So the advantage of using spot instance is like we will get a significant cost saving if the instance gets allocated. Close to around 70% we will be able to save if we are using spot instances. In case of on-demand instance, then we will be charged for the entire billing hours, for the entire training hours that we utilized. Flip side of spot instance is like, in case if there is a capacity constraint, like the instance that we requested is not available, we have to wait. And then we are creating an estimator using this PyTorch module. Here we are giving entry point as CIFAR100 PL v12.python. So if you have noticed, I have created another directory here called source dir. Let us open it and check the contents. So this one is holding the Python script that we are giving as entry point in the estimator. Then role is role, which we have attached to the notebook instance when we created the notebook instance in the initial videos. Framework version is 1.7.1, Python version is Py3, and we are giving the source directory. Source directory is /source_dir. So this is just pointing the source directory from where we should take the script and other required files. Hyperparameters. Using these hyperparameters, we can override the Python arguments that we are passing in the script. We will go through it in detail once we examine this Python script shortly. We are using instance count of 1, and we are using instance type MLP3 8x large. So this was what I was mentioning when we started this video. This is a GPU only instance, this is a GPU instance, and this instance is having 4 GPUs. So in short, we will be executing this training with 4 GPUs. And base job name, this is the job name that we will be giving, so that the logs and other stuff related to this training will get saved with this prefix in S3. This is the checkpoint S3 path. So once the training is finished and checkpoint is saved, what will happen is like, initially the checkpoint will be saved in this folder. This is the checkpoint local path, opt_ml checkpoints, and once the training is done, Sagemaker will automatically copy over checkpoint.path to this checkpoint S3 path that we have given. So if you notice, we have given the checkpoint S3 path at the beginning, and the bucket, we have to specify the bucket which automatically will be the S3 bucket we have attached here. And we are confirming that we are using spot instance. And max run variable, the significance of this is like, if we are using spot instance, the runtime should be limited. Again, you can choose to give this more than 1200, and max wait is how much time we need to wait before spot instance is getting allocated. In short, we will wait for 1210 seconds to see if spot instance is getting allocated or not. If not, then again training will terminate and we have to try again. And we will be using WANDB for logging purpose. In Google Colab example we use TensorBoard, but here we will be using weights and biases, which I felt is more powerful than TensorBoard. So we'll be giving a WANDB API key, which you will get once you create an account in weights and biases. Then they will offer you an API key, which you can give here and which you can use, which you need to pass to the estimator, so that WANDB logging and all those things will happen correctly. So before going into details, this is how we will start training. So we will just give .fit and we will pass the inputs that we just prepared earlier, that is the data CIFAR100. So we will call this fit method and the training will start. So you can see the logs. So before we get into these training log details, let us examine the Python script and see what is happening inside. So these are the customary imports. We are importing pickle, WANDB, and import subprocess. Okay, so initially I was pip installing the PyTorch Lightning using and Google Drive downloader using subprocess, but there is another way to do it. What we need to do is we need to create a requirements.txt file, and whatever requirements we need to install, we need to keep it in this file, and make sure that you are keeping this requirements.txt file in the same folder where your training script is residing. So in this case it is sourcedir, so I kept requirements.txt and my Python script inside sourcedir. So once we do this, the requirements will get automatically installed, which means I will be installing PyTorch Lightning, Google Drive downloader and WANDB. And next are required imports both from Torch and PyTorch. CIFAR100 data module we already discussed twice, once during Google Colab and second time when we started this session. Create model, this is the same thing that we have discussed during our Google Colab training. We are creating a Lightning module. One difference from what we have seen in Google Colab is like this statement WANDB.log. So this WANDB.log is what helps us to log in weights and biases. So what we are doing here is like we are logging the training accuracy and training loss, and we are passing the current epoch as well, so that we will get a epoch wise view of the training accuracy and training loss. Same with validation step, we are adding two additional statements. Test step also we are just tracking the test accuracy and test loss. Configure optimizers is same as what we seen in Google Colab training. Then we will define a function called train, which will take few arguments. We will examine in detail what these arguments are and how the hyperparameters that we are supplying here can be used to override it. So first we are creating the data module object. We already did this in our Jupyter notebook, so we are pretty much confident that things will work fine. This is prepare data, this is setup. Prepare data will download the data from Torch Vision datasets library. Setup will set up the data so that train loader and test loader can use it. Early stop callback we discussed during our Google Colab training. We will wait here for 20 epochs to see if validation loss is decreasing or not. If not, it will stop. So here, if you remember during Google Colab training, we have saved the weights of the training to a Google Drive path. So what we are doing here is we are just trying to download it from the Google Drive using Google Drive downloader, and we will do this only if checkpoint is not present in optml checkpoints. If it is not there, then rather than starting from scratch, we will load the model from the weights that we have already saved in G drive. Then these are WANDB related stuff. We are creating a WANDB logger with project name Sagemaker CIFAR100 PL5 V12. Then we are creating a trainer, exactly same as what we have seen in Google Colab training. We are going to train here for a max box of 5. Progress refresh bar rate is 20. We are using 4 GPUs because the instance that we choose to use here is having 4 GPUs. That is MLP3 8x large is having 4 GPUs. Then we are going to use strategy as DDP. DDP is data distributed parallel. This is a training strategy when we are using multi GPUs. So what will happen is like each GPU will get a copy of the model. Forward propagation will have, forward pass will happen, then back prop will happen, then the gradients will get synced, average of it will be taken, model weights will be updated, and each GPU weight will get again updated. So that is what this data distributed parallel strategy will do. Logger we are using is WANDB logger, and enable model summary max depth equals -1, same as what we have covered. Then we are doing trainer.fit and trainer.test methods. Then we are using the save underscore checkpoint, which is a method in PyTorch Lightning to save the checkpoint. After that, we will just exit the WANDB process by using WANDB.finish, and then we will save the model. Initially, this model will be saved in /opt/ml/models. Okay, this is the local directory where model will get saved with the name model.pth. If you see this model underscore directory, we can notice that we are giving it as default, that is os.environ.sm model directory. Next we have imshow function just to show the image. Then we have model fn. This function is important during inferencing. What will happen during inferencing is like when we call the predict method, it will look for this model function, and this model function, what it does is it will check the model directory and see if this specific model is present or not. If it is there, it will load the model using this one. Okay, so if you have noticed, this model that is saved is in CPU, so we will be using it for inferencing, because inferencing we are doing with a CPU only instance. And now we will keep a main guard, and we will call the training function that we just explained before inside this main guard. So here is where we are passing the arguments. We are using parser to add the arguments. So here we are using workers, epochs, batch size, learning rate, momentum, and several other arguments here. So as you can see, there is checkpoint path, which by default is opt.ml checkpoints, and model directory, which is an environment variable, but by default it will be /opt/ml/models. So what we can do is like we can override these arguments that we have given here default by passing it as hypermanager. So here we are giving batch size of 32. So what will happen is like batch size of default size 4 will be overridden, and our train loader and validation data loader will get the batch size of 32, whereas for test data loader we have hard coded it to 4, so test will be getting 4 images. Next we will do CIFAR100 estimator.fit, and as you can see, training will happen, and since we are using 4 GPUs, we can see that the model is getting downloaded and loaded 4 times. If you inspect the log, we can see this. We can see that that is what is happening. You can see that it is getting downloaded and loaded successfully around 4 times, corresponding to the 4 databases. And all these are training logs. So since we are doing it for 5 epochs, we are seeing the logs corresponding to that, where epoch number will start from 0, and we are getting a test accuracy of 57%, which happened only because we used the pre-trained model that we saved in Google Drive, or else maybe it will be hovering around 10% or 15%. As you can see, checkpoint is also saved 4 times, corresponding to 4 GPUs. This is what I was mentioning. The model will be by default saved into /opt/ml/model.pth. So this will be the one that will be used in model fn function that we explained. And this is the advantage of using spot instance. I trained for 501 seconds, but managed to get a 70% cost savings. So now it is saying that the logs are copied to WANDB as well, which we will just quickly go through after we talk about inferencing. So inferencing, we are just preparing a predictor using deploy method. We will be using the same estimator that we created earlier, and here we will be using data editor. We will be using is test loader, and this indicates that predictor is ready. And what will happen is, like, once predictor is ready, it will automatically create a endpoint as well, which you can find here. Here now it will be empty because I have deleted it, but ideally once you run this step successfully, you will see the endpoints listed here with proper names and ARN. Here we are calling the data iterator and passing 4 images and seeing how the predictions are. So as you can see, ground truth was cloud, apple, C, skunk, and prediction is cloud, apple, bridge and skunk. So for a 57% accuracy, looks okay. And after that, I am just deleting the endpoint. This is the reason why you are not able to see it here. Reason why I deleted is, like, I'm not planning to use this endpoint anymore apart from demonstrating this in the video. So if I'm keeping this endpoint, maybe I will incur some cost from AWS end. So rather than just incurring the cost unnecessarily, I just thought of deleting it. So I would recommend you also to do it in case if you are not planning to use it in future. Next step, what we are going to do is just check whether the checkpoint is working correctly or not. If you remember, we mentioned that if checkpoint is present in this folder, it will load the checkpoint from there. If not, we will load it from Google Drive. So first time when the model was training, there will not be anything inside this folder. So it downloaded from Google Drive. So now we are going to train it again. This time we are expecting this checkpoint.pth to be present here, and I just want to make sure that it is successfully getting loaded via this load from checkpoint method, which PyTorch Lightning offers. So after typical downloads and everything, yeah, we can see that checkpoint path found and model is loaded successfully from opt.ml checkpoints. So again, we can see these corresponding print statement 4 times because we are using 4 GPUs, and training happens successfully, and we can see that completion method and managed to get a 70% spot training saving, which is good. So this is in short how Sagemaker training is happening. And one good practice you can follow is, like, once you are done with your training, maybe you can just stop this instance. You can just click here and stop it. Now we will quickly go through weights and biases to see how it looks like. So if you remember, I have given the project name as Feb5v12 when I created the WANDB logger. So we can see a lot of charts here: test accuracy, train accuracy, and we can check it epoch wise or step wise. There are various x-axis options. So I have actually used this project for 2 runs. First for our initial training, and during the second run when we are checking if checkpoint is working correctly and or not. So we can see the corresponding plots. And another thing is like we can see the system related aspects as well. So it is showing the GPU power usage. So we are seeing 4 plus 4 8 curves here corresponding to 2 trainings using 4 GPUs. So weights and biases I felt is having more information compared to TensorBoard logger, and it is quite easy. Just create a account and you will get the API key, and after that we just need to do some additional logging and few more parameters to be passed to our training script, and should be good. So that concludes our session, that is training and inferencing in AWS Sagemaker. So in short, we created a notebook instance, then we created a notebook inside it, we prepared a Python script, then we passed, then we created a PyTorch estimator. Through the estimator we called the Python script, we made sure that checkpoints are saved, and we also created a model function so that our predictor function can load the model during prediction. We used WANDB logger. After that, after the training is completed, we created a predictor, and using this predictor we call the predict method, which in turn called model function, which we defined in our Python script to load the model, which is a CPU only model, and did the inferencing. After that we just ran one more time to ensure that checkpoints are being fetched correctly from the local checkpoint path, and that it is getting loaded correctly. So that's all regarding Sagemaker training with multi GPU instance. Thanks much for watching.